yeah, the second semester of this class is a lot more statistics focused. So like most of the notes that I'm gonna be writing about are all statistics, because it doesn't really matter whether or not you know probability anymore, other than some like conditional probability stuff. So yeah, I guess like the first thing that we should probably cover is some basic rules that we will need time and time again. So first things first is that the linearity of expectation, so expectation of ax plus by, where a and b are constants and x and y are random variables, equals to a, the expectation of x, plus b, the expectation of y. So this is just one rule. Another rule that we will have is that if x and y are independent, we will have that the variance of x plus y equals to the variance of x minus y, which equals to the variance of x plus the variance of y. So it doesn't matter if you're adding it or removing it. By having it in as part of the equation, you're increasing the total variance of the thing, which is why you would have this, which is why you have this to be true. Can you see it actually? Like, if this is not working, I could, okay, great. Because I noticed a reflection, so it might be a little bit hard to see. If it's hard to see, I can move down to a blackboard somewhere else. Okay, and I guess like probability density functions, cumulative distribution functions should all be like fine. Some very important definition is that a random sample is a situation where each member of the population is equally likely to be chosen. So everyone is chosen by chance. And that's how you like randomly pluck a few people from a big population to do a test. And the reason why you would want to randomly pluck a few people from a big population is that if you're trying to, like, let's say if you're trying to see if McGill students are stressed right now, you can't possibly go and like interview every single McGill student out there, right? But then what you can do is you could try to create a random test by trying to randomly pick a bunch of McGill students. So maybe like you have a random number generator and you like select students by their IDs, and it's just randomly selected using that number range. And that would be a way to get a random sample. What wouldn't be a random sample is if you went to Roddick Gates at 8:30 a.m. and asked everyone who was there, because then you would have people who are conscientious and show up to class. So that's where like the idea of a random sample is really important, because it will be consistently used again and again. When you're like trying to test something out, you just take a small proportion of the whole population and you test on them. And yeah, okay, so I guess the next thing we should probably cover is covariance. So covariance is going to show up time and time again. So especially in the correlation coefficient and stuff like that. So it's important to know that this is the definition of covariance. So covariance equals to the expectation of x minus mu of x times y minus mu y. So generally, when the covariance is greater than 0, this means that they both move together. When it's less than 0, it means that they move in opposite directions. So when x is further away from the mean in the higher part, y is going below the mean. And then when it's equal to 0, that's usually when it's like completely independent. And so we actually have that, yeah, based on this, you can tell that if you have covariance of x with itself, then you actually get the expectation of x minus mu x squared, because y is replaced by x. And then now we have that this is the variance of x. So I'm not sure how much like theories and proofs that Saraswata went through, but this shows up quite a few times, at least in my year. And then another thing that is important is correlation. So the correlation between x and y is the covariance between x and y divided by the variance, like the standard deviation of standard deviation of x and the standard deviation of y. Why do we do this? It's because basically we want to scale it back down, right? So the situation over here is that covariance of x and y can be high, but like it can be high for different reasons. So let's say the variance of x and y are just naturally high. So even if there's not much of a good if there's not much of a strong correlation between them, covariance can be still made like artificially high if this value or this value is high on its own. So this is why you divide it by this. So this is the, and so this like basically normalizes it to be like less than or equal to 1, less or equal to -1. So that's how you normalize it. Okay. And then something that's super duper important, but also not something that I am very good at remembering, but this is basically like the foundation of every single t-test out there. You need to remember is that sample variance. So sample variance is s squared, which equals to 1 over n minus 1. And then you take the sum to n, I equals to 1, xi minus x bar squared. So the reason why you would look for this sample variance is this is an unbiased estimator of sigma squared. So what does it mean to be an unbiased estimator? An unbiased estimator is where the expectation of s squared minus sigma squared equals to 0. So you're not, can you, sorry. If you send it to me afterwards, I'll go through it, but probably just like a refresher first. So I guess like the important thing is that over here, like this is considered an unbiased because there is no consistent, like you're not consistently saying that, oh, this is more than sigma squared. You're not consistently saying it's less than sigma squared. So this is why this is the definition of unbiased. This extends to more than just variance. You can also say that the sample mean is an unbiased estimator of the population mean. And in that way, like that also makes sense. Because yeah, like the expectation, like if you take many sample means and you take the expectation, it equals to mu. So yes. And so that is why this is important, because knowing the population mean is much like we can estimate the population mean from x bar, right? But then how do we estimate the population variance? We need to use s squared. And x bar, it looks like a much easier and more intuitive formula where x bar equals to 1 over n the sum xi. So it's like if you've ever taken any average, this formula makes a lot of sense, right? This formula looks less intuitive than this, but this is the formula that you need to remember because you're going to be using it a lot. Yes, okay. And I guess like when you have sample variance, you also have sample covariance, which is where, if you remember regular covariance, how does it erase this? If you remember regular covariance, then you would know that sample covariance, like let's say sample covariance. If I'm extrapolating in the exact same way, I just tag on an n minus 1 at the front, and then I take the sum, and I equals to 1, and then it's xi minus x bar, yi minus y bar. So in that way, it's kind of similar to the like regular covariance, which had like xi minus mu x, yi minus mu y. The reason why we can't use this regular version of covariance is that what is mu x and what is mu y? Well, we don't know, right? So it's kind of problematic when you don't really know. And you can try to estimate it with X bar and Y bar, but there's going to be some systematic, like, it's going to be systematically off because you lose 1 degree of freedom, which is why you need to divide it by 1 over n minus 1. And I guess in that exact same way, you have sample correlation, which is a nice value R, which you're going to see a lot when you're doing regression later. So this is 1 over n minus 1. See, same thing again. And then this would be sample covariance. So this value divided by the sample standard error of X and the sample standard error of Y. And if you know this, you would know that this would be between, again, 1 and -1. And this, yeah, this will come back later. But for now, this is like the stuff that you need to know. Do you need Chevy Chevs? I think that you don't really need Chevy Chevs. Like it's fine without it. Okay. I guess now we can move to distributions. So there are some very important distributions that you need to know, and some not so important distributions that you don't really need to know. So I'll just write them all at this side, and then I'll tell you which ones are important and which ones aren't. So the first one is the uniform distribution. The second one is the Bernoulli distribution. The third one is the binomial distribution. Fourth one is Poisson. The fifth one is exponential. Sixth one is normal. Then we have the student t distribution, and then the chi-square distribution. So the first thing I'm going to write is this important? And then I'll tell you exactly where it's important. So this one's also important. This one is important because you're going to need it whenever you do population proportions. So if you've seen like some of the regressions where or hypothesis tests where you do population proportions, like how many people voted? No, how many people voted? Yes. So that would be a situation of like a Bernoulli. You're going to need to use some facts from Bernoulli for that. Binomial, this is usually not important, as long as you remember that if you do enough tries in a binomial, the sample mean, sorry, this should be a bar. The sample mean will become similar to the normal distribution. Well, the sample mean like this, like the standardized sample mean. So beyond a certain point, you don't really need to know how to do a binomial anymore. So Poisson, not really that useful. Exponential, not really that useful. And then these three are the most important things. So normal is useful for whenever you do your z tests. This is useful for the central limit theorem. And yeah, I guess like also normal is also useful in that like linear combinations of normals are normal. So if you have your original sample being normally distributed, X bar will also be normally distributed because X bar equals to 1 over n like this, right? And all of these are normally distributed. So you have a linear combination of normally distributed things. So X bar will also be normally distributed with like mu sigma square over n. And that's why you can do some of the tests that you can do. But then, I didn't write a T. Okay, but then why do we need a student T distribution? The issue with normal is that you can kind of see here that they assume that you know sigma square. And assuming that you know sigma square is really not great because it's okay if you don't know mu because that's what you're trying to find out. But assuming that you know sigma squared is not true because most of the time you don't know what the underlying, like unless there's some like, unless the question gives it to you. But even when the question gives it to you, it's kind of ridiculous, right? How would you know the true population sigma squared of something? It's kind of really not possible to know. And so this is where you use student t-distribution. So student t-distribution is when you use S squared instead of sigma squared. But then because you're using a kind of like a wonkier version of sigma squared, it's less reliable, right? So it's going to be much more conservative. But as n goes to infinity with the student t-distribution, where there's a degrees of freedom parameter, right? So the degrees of freedom parameter equals to n minus 1. So as n goes to infinity, your sample variance also gets more and more and more accurate. So as n goes to infinity, the student t distribution n minus 1 goes to normal 0, 1. So it's basically just saying like the wonkiness from having S squared over there, like the error that you get is smaller and smaller and smaller as n goes to infinity, because as n goes to infinity, you get more information, right? So when you get more information, your sample variance is just more accurate. And since that sample variance is more accurate, you get a better test. And that is, but we still can't say it's an exactly perfect test, because a perfect test would look like us knowing exactly what sigma squared is. And so chi-squared is important because if there is something else that where it's n minus 1 s squared over sigma squared, this is chi-squared n minus 1 distributed. Okay, so the reason why we would care about the chi-squared and care about these extreme values is because how do we know what range sigma squared is in? So now we have a distribution. We know S squared and we know n minus 1 because we were running the experiment. So when we were running experiments, we could control and see how many n we have. When we were running the experiments, we can collect all the data that helped us calculate S squared from that like formula that I gave you just now, which is really important. So if I know that it follows this distribution and I know this and this, then I can kind of figure out what sigma squared is now, right? So these three most important. This one kind of important, the rest you can do without it. And so here's like the important thing you don't need to know from Bernoulli is that mu of Bernoulli is P. And then P is the probability of getting 1, right? So it makes sense that the mean is P because like the population, like the population mean is P because like if you get n minus P zeros and then you get P ones, then like this will be P times 1 plus n minus P times 0. And so then we would have that this is the mean, right? And so that's why the mean is P. And then in the same way, we would have that the sigma squared of a Bernoulli distribution, where you know the Bernoulli distribution is P times 1 minus P. So these are the important things that you need to know for you to do the population, like proportion of the population stuff. Because in order for you to run the test, you need to know what mu is, and you need to be able to estimate sigma squared. So your estimate would be this and this. And that's the most important things that you need to know from there. Yes, okay. Is there anything else? No. Okay. I guess we will move on to, yeah, okay. We'll move on to estimation, I guess. Also, if you have any questions, you can stop me at any time. Like, if anything sounds weird or like doesn't really make sense, I'm like here to answer your question. So okay. So I guess like, yeah, so just now we already covered bias, but I'll just cover it again. Because so bias of estimator theta hat. So theta hat is an estimator, theta hat is an estimator of theta. So an example of what theta hat would be is like how x bar is an estimator of mu. So whenever you say something is an estimator or something, this thing is something that you have to be able to know. So if you give a quantity that you can't exactly ever figure out, like mu, then it's kind of useless for you to have it as an estimator, because the whole point of an estimator is that you're able to gain more knowledge about mu from knowing x bar. So you need to be able to know x bar. So the bias of an estimator theta hat would be equal to the expectation of theta hat minus theta. So same thing as just now. So the bias of x bar equals to the expectation of x bar minus mu. And then since we know that x bar is distributed by, like with the central limit theorem, you would know that this is true. Either that or if it's normal. So then we would have that this equals to 0. So then when the bias is 0, then you can call it an unbiased estimator. And then I think it's also important for us to discuss, when do you need what thing? Because there's like a million different types of tests out there, and it's kind of annoying to sort through everything. So I guess like I should probably go and cover that first. So the first condition is 1. Is your original sample the normal distribution? So if your original sample is the normal distribution, then you don't really need to use the central limit theorem, because as we said just now, x bar is also normal because it's a linear combination of other normals. And so here's where you don't need the central limit theorem. The only thing you need to know is, after this question is like you say yes, then the next question you need to ask yourself is, do I know sigma squared? So sometimes the teacher magically gives you sigma squared and then you can use it and it's perfect. Then fine, you can use the z test. And I'll cover the z test later, but it's basically the situation where like x bar minus mu divided by sigma over square root of n. This follows the normal 0, 1 distribution. Okay, if you don't know sigma squared, let's say, no, I don't know sigma squared, then you have to estimate sigma squared through s squared, which introduces problems, it introduces bigger errors. So if no, then what you have is x bar minus mu over s over square root n. Over here, you notice that there's an s here. This follows t n minus 1. So this goes down this tree, you find like all the different conditions, and then this is okay, right? What if your original sample is not the normal distribution? So this is where we have something magical called the central limit theorem. So the central limit theorem effectively says that if n is large enough, I think the arbitrary boundary they gave was n is greater than 25, then your x bar will converge and distribute. Okay, well, x bar minus mu over sigma squared over sigma over n converges in distribution to normal 0, 1, right? So that's where you say like by the central limit theorem, since n is large enough, then we can say that this converges to this distribution. But that's assuming you know sigma again. So if you don't know sigma, then what you have to do is you have to use the central limit theorem. And then after that, you say that this converges in distribution to Tn minus 1. And so that's why you would use the central limit theorem. So I think the biggest like mistake that people tend to make is that, actually, no, I think you need, I don't think that this is allowed, sorry. Only this. So you have to know sigma. But I think the biggest mistake that people usually make is that when the original sample is already normal, they use central limit theorem. But you don't need central limit theorem in that situation because x bar is already like normally distributed. And so like the definition of T as a distribution is that you have a normal 0, 1 distribution divided by a chi-squared distribution below. So like you need that this is normal 0, 1 in order to use the T. Yeah. So I guess like this is your path to figuring out what test to use. So you just follow the path and then it should be fine. And after that, you shouldn't have any problems with regards to tests. Okay. I guess I'll erase that now. Okay. So next thing I want to cover is efficiency of estimators, but very briefly, because I don't think that they really care that much about it. But if you do econometrics in the future, you're going to need it. So then like, let's say you have two unbiased estimators, right? So they both don't introduce any like bias just by the estimators themselves. So how do you tell if one estimator is better than the other? So here is where you would say that, so this is estimator number 1, theta hat 1 is more efficient than theta hat 2 if the variance of theta hat 1 is less than the variance of theta hat 2. If you think about it, this actually makes a lot of sense because they're both like, you're both giving an unbiased estimate, like they're both giving unbiased estimates because these are both unbiased estimators. It's just that this is more consistently giving it more like closer to the actual value. So that like, let's say this is the actual value, right? This is theta. And then you have one estimator that like does it like this. And it's like, it's unbiased, but it's very spread, right? And then you have another estimator that's like this. This is like way more concentrated at the actual correct value. And that is why that estimator would be considered more efficient. Yes, okay. So.
Sorry, Tiffany?
Yeah.
Is there a mechanical proof for this, what you just showed, like in terms of the graph and
Oh, is there a mechanical proof for this? This isn't a proof because this is a definition. There is 100% many mechanical proofs to show how one estimator is more efficient than another. And that's where you have like a least unbiased estimator, like no, best linear unbiased estimator. So there's a class of estimators called best linear unbiased estimators, where how do you define it's the best linear unbiased estimator? It has the least variance. But this is just a definition. You get what I mean? Like you want to be able to choose between a few different estimators. How do you decide that one estimator is better than another? This is one of the qualifications that makes you say like, oh, okay, this estimator is pretty good because it has a very low variance.
Yeah, he went over the blue or whatever, what you just mentioned, in terms of the best linear.
Oh, he went over blue?
Like I don't think it'll be on the exam, so, but
Okay.
he mentioned it.
This is like you cover it in econometrics, but there is a theorem called Gauss-Markov that like under very specific circumstances, you can say for sure that there is one like estimator that is the best linear unbiased estimator. But I don't think that that's content that's going to be on this exam. So I'll just focus on the stuff that's going to be on the exam. Okay. Okay. Yeah. I guess like something else is that you remember when I said that X bar is distributed normally with like this. So this is like most of the time. And the reason why we say it is most of the time is because there's a situation where it isn't. And this is only true when the sample, this sample n, is large relative to the total population big N. The book didn't give a very specific like estimate of like what is considered large with respect to, but let's say you have a super tiny population of like N. Like let's say you're trying to figure out like the whole city of Montreal's like income, and you ask like 10 people. So that's something that's like it's a very small proportion of the actual number of people, right? So, but if we assume it's normally distributed, you can still say that X bar is normally distributed because the formula that it's a linear combination of normal things still holds. The only adjustment that you need to make is that you must multiply this by n, big N, the population N, minus small n, my sample N, minus big N minus 1. Yeah. So this is your finite population correcting term. The reason why this works is because they're assuming that like, oh, okay, it's a huge proportion of the population, so it's a good estimate. If you have a small proportion of the population, you need to like rectify your estimate by multiplying this. And so so let's say if in your exam question he asks, so let's say we have a sample that is a small proportion of the population. You do the exact same test with X bar. It's just that you multiply it by this. And that's all. Yes, Sarish?
So he said that he wouldn't ask us a question with finite population correction. In the exam, there was an example where it would be used, but then he wrote in brackets, imagine you had a finite infinite sample size. Like,
yeah, okay. Yeah, generally a lot of these things are also like, yeah, I didn't really manage to ask him exactly what tested. He just said everything until I messaged him and he said everything until chapter 12. So I just like generally went over everything until chapter 12. The next thing that you should definitely know is something called a confidence interval. And so the confidence interval stuff gets very repetitive as soon as you kind of know the structure of the situation, right? So confidence so I guess I'll just kind of like write it through once, and then I'll just show you how you can plug in everything back into the same formula again and again. So it won't really be a problem. So first thing, let's say X bar minus mu over S divided by square root N. Okay, I'll use a small n here. Small n. We know this distribution, right? So how do I find with like, let's say 95% confidence, I want to find the interval where mu lies, right? So let's say like there's a distribution of mu somewhere, okay? Mu is this like, this mu is this normal distribution. I want to be able to find the values here and here, where everything beyond this is 2.5%. Like you only have a 2.5% chance of mu being beyond here. And you only have a 2.5% chance of mu being beyond here. Okay? So this is what is called a two-tailed test. So well, not really a two-tailed test. This is what is called like a confidence interval. So where I want to know this to this. Because without being given any other information, then I'm forced to assume that mu can be anything from minus infinity to infinity, right? But then let's say I'm trying to say like, okay, I don't mind if I'm wrong 5% of the time. I just want to know if I'm only wrong 5% of the time, how many, like, what is the range in which mu will lie? Because if you don't allow if you want to be 100% of the time right, then you will have to go from minus infinity to infinity. Because it is exceedingly, exceedingly, exceedingly rare, but it is possible that one day you're going to find something that's like a ridiculous number and super low or super high. So that's where you have the problematic tails, right? So this is where if you want a 100% guarantee, you get no information. If you only want a 95% guarantee, then all you need, then you can find there is a bound over which like 95% of the values lie in this middle portion. 95%. And that's how you construct the confidence interval. And since you know the distribution of this, so then let's say that this is a Tn minus 1 distribution, which equals to x bar minus mu over s over square root n. So if I just multiply these values over and I change the sign, then I can isolate a value for mu, right? So like maybe that was a little bit confusing, but I'll move through the confidence interval thing first. So the first things first is that you need the probability by definition, right? So you need the probability that you're going to lie in this range. So minus q 0.025 less than x bar minus mu over s divided by square root of n less than q 0.025 equals to 1 minus 0.95. This is basically saying that I want the, sorry. So this is basically saying that I want the probability that it lies in here to be 0.95, where this is the alpha level of significance, right? And so this is where the reason why I put q 0.025 and minus q 0.025 is because I can do that given that the t distribution is symmetrical about 0. So I could change this one to 1 minus 0.025, but it doesn't matter because all it would be is introducing the minus sign anyways, because it's symmetrical. So if you have something that's like here and here, this is like 0.025, and then this would be minus 0. Like the bounds are symmetrical around the axis, so it's fine. And over here, the Q stands for a quantile. So Q is actually just the critical value beyond which it would be the critical value exactly as I drew just now, where, okay, I should actually stop erasing drawings so that things make more sense. But so over here, where it's 2.5%, this is Q. Right, over here, it's 2.5% again. Since it's symmetrical about 0, this is still Q. It's not symmetrical with the way I draw it, but it's like, pretend it's symmetrical. So this is the quantile, right? Beyond which like there's only 2.5%. And so the way we solve this is by literally just rearranging it. Because we know that this is the Tn minus 1 distribution, right? So we can get these values. This is Tn minus 1 0.025, like minus. And I'm not sure if how he asks you to do them, but there's a table where you can read these values off. So over here, this is Tn minus 1, 0.025. So we know these values. And then we know this value, and this value. So then we can find the bound on this. This is basically how it works. So we have that the probability that you lie in between Tn minus 1, 0.025 multiplied by s over square root of n is less than x bar minus mu less than minus Tn minus 1, 0.025 s over square root n. This probability equals to 0.95. So the probability that this lies in this range is 0.95, which is exactly what we wanted in the first place, right? And so now we keep expanding and then we rearrange it. So like since this is a minus, we like flip it over. And so, but since it's symmetric, it doesn't matter. So over here we have minus Tn minus 1, comma 0.025 s over square root of n less than mu minus x bar less than T n minus 1, 0.025 s square root of n. This still equals to 0.95, right? And then now all I need to do is add it on the other side. And on both sides, like add it and expand it, and we're done. So the probability that it lies in this range, minus Tn minus 1, 0.025 s times square root of n x bar plus Tn minus 1, 0.025 s divided by square root of n. So this probability is 0.95. So now we have found a bound where you found this value of mu to lie in between these intervals with 95% probability. So that's where you can say that my confidence interval is that with 95% probability, mu is in x bar plus minus Tn minus 1, 0.025 s divided by square root of n. So this is your confidence interval. And like if any part of that didn't make sense, you can feel free to ask now. Oh, Suresh, I see if your hand up. Oh, okay.
Sorry, that was my access from before.
Oh, okay. Yeah, okay. So yeah, this is our confidence interval for mu. But you see that like I chose a few like arbitrary numbers, right? So I chose a 95% confidence interval. What if I wanted like a 90% confidence interval? A 90% confidence interval looks like over here, you have a smaller number. Which means that like I'm willing to be wrong more times as long as I have a tighter interval. Because if I'm willing to be wrong all the time, I'll just pick any random number, right? So if I'm willing to be wrong more times, that means that this tail becomes fatter, it becomes 5%, and this other tail becomes 5% as well. And then the only thing you need to change is the alphas. So over here, this would be like the level of significance equals to 0.1, right? Because this is how many times you're willing to be wrong. So this is how many times you have to be right. And so what you will be changing is over here, you change this to 0.1. Over here, you would change this to 0.1 over 2, 0.1 over 2. Every time you see one of these, it's 0.1 over 2. So the general formula is that this is alpha over 2. So this is alpha over 2. And this is how it works for a two-tailed test, because you're allowing for equal weights to be wrong on both sides. That's why you need to divide alpha by 2. So over here, I'll change this to alpha over 2. alpha over 2, alpha over 2, and alpha over 2, and this one is alpha. So this is 1 minus alpha, right? And not only that, but you can still further generalize this. So over here, we use the t distribution, right? So what if we actually have sigma? Another thing that we know is that x bar minus mu over sigma divided by square root of n is following the is following the standard normal 0, 1. Right? So the only thing you would need to change in between this situation and that situation is instead of using the t-test like bounds, the t-test like definitions, you use the z-test definitions instead. So this is where you would use z alpha over 2. This would also be z, and you would do the exact same procedure. Exactly the same, nothing has changed. You just like replace this number with the number you get off the normal 0, 1 table instead of the t-test distribution table. The same thing for chi-square. So it's like it's kind of a repetitive process, but basically like the only thing that changes in between is like what is your alpha to get your extreme values? What kind of test are you doing to get those extreme values read off the table, right? So over here, like when I say 2.5% is to this side, that means that it's based on the distribution that I have. If I had a different distribution, like let's say a chi-square distribution, where it's like this, then 2.5 looks like being over here and over here. And now you can see that it's no longer symmetrical, right? So under that circumstance, that is where I would need to replace this with chi-square n minus 1, comma 1 minus alpha over 2. So but basically the same principle remains throughout. You have something that you know the distribution of. Since you know the distribution of this something in the middle, then you can find the bounds on the upper bound and the lower bound on this thing. And then you solve and solve and solve and solve until you get a confidence interval. Does that make sense? Yeah, okay. So I guess like some other, did he say if he was going to cover mean difference on the final? Okay, I assume that he will, and I will cover mean difference then.
Can you go over what that is just to make sure? Because maybe if we look at it, maybe we'll know, just in case.
So yeah, mean difference is basically a situation where you're trying to get the population means change in paired data. So it's like a before and after scenario, right? So you want to see like if I how much of a change was there before I took this weight loss pill and after I took the weight loss pill. Then that's where you would use, sorry? So that's where you would use like mean difference.
It's like a independent or dependent sample or something like that of.
Yes. There is one that is dependent samples and one that is independent. Will it be covered on the final?
We did that.
And yeah, it was pre-midterm, but it could be on the final.
Okay. I guess like I should probably speed through this part then, if it's all pre-midterm. Can you tell me what was after the midterm, and then I'll mostly focus on that?
So we started after midterm just with the proof of the line of best fit and how we get the B1 and B0 equations based off the minimization formula. And then from there, we went on to do all the variance and
the
SSE,
estimators.
the ANOVA table, all the proofs for everything in the ANOVA table, things of that.
I guess from now on, can I just skip over the hypothesis testing part? Because hypothesis testing is exactly the same thing as constructing a confidence interval. It's just that you create a hypothesis and you say, is this true or is this not?
Yeah, for sure. Just from pre-midterm stuff, can you go over the type 1 and type 2 error proofs?
Yes, there is a very good way to visualize type 1 and type 2 errors. So basically, type 1 error. And then type, a very simple way to visualize type 1 error and type 2 error is that, let's say that here is the truth, and then here is our decision. So over here, when you fail to, like, over here, the truth is that let's say, when it's H0 and H0, our decision was right. When it's H1 and H1, our decision was right, right? But then when our decision is that it's actually H0, and then we fail to reject the false null, this is type 2 error. When our decision is that it's H1 and we reject H0, but the truth is that H0 is correct, this is type 1 error. So if you think about it in this way, the perfect test looks like this. Over here, you have a boundary. Okay. And then over here, this is everything that lies in the null hypothesis H0. And this is everything that lies in the alternative hypothesis H1. So over here, let's say we reject here. Sorry. Accept here. And then we reject up here, right? The best kind of test would look like this, where you follow H0 here. As soon as you hit the boundary, you jump straight to rejecting H1, like rejecting the null hypothesis when you know it's under H1. But in reality, it's very, very difficult to find a test like that, right? In reality, you'll have a test that looks like this. Okay. A test that looks like this. And so like that, yeah, this is basically what the test would look like. There, along the very extremely boundary values, they can't really tell if the null hypothesis is correct or not. Only as the values get more and more and more extreme, then the test is like, oh, okay, this is definitely that the null hypothesis is false. Does that make sense? So what looks like type 1 error looks like rejecting the true null, right? So over here, the situation of type 1 error would be when you reject this. So this would be the distance of like type 1 error. So over here, this is the distance of type 1 error. Here, this is the distance of type 1 error, like that. And then type 2 error is failing to reject the false null. So when you fail to reject the false null, it's all of these distances. So I can give you a situation where I can completely minimize type 1 error and I will blow up type 2 error. So type 1 error, I can completely minimize the probability of rejecting the true null if I decide to accept everything. So it's like imagine that you're taking an exam, right? You want the good students to be able to like perform well, and like, but you don't want to fail, like accidentally fail any good students. A way that you can get around accidentally failing any good students is you just pass everyone. But then this results in like a lot of like not so good students also getting passed and like and then passing as well, right? And so the exact opposite of that is that you create an impossible exam. It doesn't matter if you're a good student or a bad student, everyone's gonna fail. But then the problem is that you're failing to like reject the like bad students. Like sorry, you're rejecting the actual good students. So over here, rejecting the true null is like rejecting the good students. Failing to reject the false null means like when you have a super easy exam and then you fail to like reject the bad students from passing. Does that make sense? Yes, go on.
Yeah, so like in the exam, he literally says like show that the decision rule that you have used and then like from the hypothesis test will lead to a test whose probability of type 1 error will converge to 5% if you had an infinite sample size.
Yes.
And like he doesn't so like and then it's like a long proof. Can you just go over that proof?
Let me think. Is it a long proof? Oh.
It's not too long, but like there is it's a tough proof, I guess.
Off the top of my head. Let's see. Okay, the problem is that I took a statistics class this semester and I don't know what is considered allowed for you to be able to use and what like is considered my knowledge anymore. If you show me the proof, I can go over it very quickly.
Okay. 1 second. We'll send you a screenshot.
I can project.
Yeah.
Or yeah, project the screen.
Basically how it works, basically how a proof like that would work would be saying that since you have the probability of rejection given that H0 is true. And so what you want to do is you would plug in your probability of rejection given that H0 is true, and then it should all solve itself until this becomes 0.05. And this is how it like, yeah.
Yeah, we could share our screen as to what he did in the midterm.
Sure. I guess like, does everyone like want to see this, or would you rather if I went over regression? Okay, sure. I guess like you can send it to me and then I'll.
We can share our screen. I mean,
You can send it to me over the chat.
Okay, yeah, we'll take a screenshot.
Yeah.
Yeah, at the end you will end up with alpha.
Let's see. Did you send it over the messenger chat or the Zoom chat?
No, we're sending a screenshot in right now. Yeah, right there.
Okay. Let's see. Ah. Okay. Given that H0 is true, then that would be, yeah, okay. So how this works, the reason why you split it up, if everyone could look at the screenshot, I guess. And I hope that everyone like finds this like confusing so that like, yeah, so that like I guess I can help in this way. So this is what we're looking for, right? So this is the probability of type 1 error. You're rejecting with a true null. So what does the rejection condition look like? This rejection condition equals to, I guess for this you use the proportion of the population, right? So proportion of the population minus proportion not divided by, okay, hat 1 minus p hat over n is greater than d alpha given that H0 is true. So this is just the formula that we use for like proportion of the population situations, where the reason why it follows the normal distribution is because the sample, you assume that the sample size is large enough and then it's just given to you, right? Crucially, the thing is that we don't know P naught, but we assume that H naught is true, right? Sorry, we know P naught. Yeah, we know P naught, but we assume that H naught is true. But then we want to find this in terms of P. And so what we do is we split this up into P, like this equals to P naught plus P minus P minus P naught. Like, okay, minus P plus P minus P naught. So basically, I'm creating a minus P and plus P inside here artificially, right? And the reason why I'm trying to create this artificially is because I want to get to the value of P itself. I don't want to get the value of like my estimate. I don't want to get the value of my estimate. I don't want to get the value of my bound. I want to get the actual value of P, right? So I minus it and I add it back again, and then I divided by n. This is greater than z alpha, given that h naught is true. But what is the condition that h naught is true? The condition is that p equals to p naught, right? Is that the hypothesis test? Is it equal to or less than or equal to? Okay, it's equal. Yeah. So this is the condition, right? So if p equals to p naught, then I can cancel out both of these things, because what I'm doing here is plus p minus p. So I cancel. Make sense? And then from here, what we have, this equals to the p minus p over 1 minus p over n greater than z alpha. And then yeah, and then I guess from there you can just like expand it. Like does that oh, there's a second screenshot. Okay, let me see. Slutsky. This follows N01. Let me see how it follows N01. Give me a second. Okay. Ah. Okay. You're basically trying to get, this is all in terms of p hat, right? You want to get it in terms of actual p so that you can use the central limit theorem on it. Because the reason why you would be able to use the central limit theorem on actual p is because this would, like, actual p would be, remember I told you how Bernoulli is important? Bernoulli is important because the sigma squared of Bernoulli equals to p1 minus p. So as soon as you get the actual values of p, then you have something that, then you have the actual value of sigma squared divided by, like, square root of sigma squared divided by n. So what you have over here is p divided by p minus p1 minus p divided by n. And then I multiply this by, so since I kind of arbitrarily created this, I need to remove it again, right? So 1 minus p over n divided by square root p 1 minus p over n. This is greater than z alpha. Does that make sense? The reason why you're putting p and 1 minus p over here is because when you have the hat, it's not actually the real value of sigma squared. But when you don't have the hat anymore, then it's actually the real value of sigma squared. And so that's where you can say that, okay, I guess like this converges to 1. And I would say that that's fairly, I don't know the exact reason why he says by continuity. I would say that I think that that's fairly intuitive given that this p hat is an estimator of p. So I would say that would make sense. And then over here, as n goes to infinity, we would have that this converges to normal 0, 1, because this is exactly the formula of x bar minus mu divided by sigma over square root of n. Does that make sense? So then this would be probability of normal 0, 1 greater than z alpha, which equals to 0.05. Well, not 0.05, sorry, alpha. Does that make sense? Darish? Okay, if that's good, I mean, like, if you have any other questions, you can feel free to ask as well. Or like, if you want any clarification on this, because yeah, this is a pretty tough question. I don't think I would have gotten it. But yeah. I guess if this is all right, I will just move on to regression, because I would be more concerned that that would be on your exam at this point.
Just one thing about the thing we did. What is continuity exactly? Continuity, like, as a theorem, or I don't know, like.
What is continuity in terms of econ or in terms of math?
In terms of like how that, why does that become one? Like, or why does it equal one at the end?
Let
By
me-
continuity.
That one, I might not be so sure, but I can take a look at it and think about it for like one. I think maybe in a minute, I would be able to figure it out. Continuity, if we have a probability that P is greater.
It's okay. Don't worry about it. We'll
The
figure
way
it
that
out.
I would see it is that since if you assume that P is not equal to 0 and not equal to 1, then neither of the values you won't have a 0 denominator. And since you don't have a 0 denominator, then the P hat minus P hat multiplied by 1 minus P hat, since it's an estimator of P and it's an unbiased estimator of P, since as you go to infinity by the continuity of probabilities, you would have that P hat is getting better and better at estimating P. So the actual value of P won't deviate that much further from P hat. And so if P is equal to P hat and like 1 minus P equals to 1 minus P hat, then you would have that equals to 1 inside, and then we give the square root of 1. I think. I would definitely ask him this, and like if you want to tell me about it, you can feel free, because I'm also interested. But like my best guess is that this is just that since like P hat is your estimator of P, and this estimator is based on data, as your data sample gets larger and larger, and since your variance will get smaller and smaller, right? So it will follow a tighter distribution. And so as your sample goes to infinity, that gets better and better at estimating the real population values. Does that make sense?
Yeah, thank you.
Yes, okay. So I guess like for regression, I didn't manage to prepare much for this, but I think the most important thing about regression is that you have a good intuitive understanding of what like a regression is actually doing. So I guess like the most classic example of regression is where you draw like a three-dimensional diagram. And so this is where you draw this, and then this. Okay. And what your regression term is basically doing is that you have this like 3D diagram somewhere, right? Like this is your actual data point. Okay. And it can only tell like over here where it is. So over here you have this unavoidable error term. Because you don't have since it's lying above this plane where like let's say this is x1 and this is x2. So using only x1 and x2, you can't figure out this is everything else. Right? So over here you have like x1 and x2, you can explain quite a bit, but you can't explain everything. So the part that you can explain is the well, when you sum up together everything that you can explain, this is like the y hat. This is the explainable part. And then this is the unexplainable part, which is y itself. So that's where you have the error term, and this error term will never go away. Like it's not possible. But there is a difference between this error term and this error term, where this error term is like a natural property of the thing. And then this error term is just based on like our estimates are not as great. So this EI would be yi minus yi hat. So this is the consistent like wrong estimation of our data. So this EI, like this epsilon I, consists of both this EI and some randomness. So let's say UI. So this is like the perturbations. You can't really get rid of these perturbations. If you got rid of these perturbations, it would be completely deterministic of the model, which wouldn't be good. So like, yeah, I guess, yeah. And so I guess like there are many different examples of regressions. Like the first thing I want to like give an example of regression is like, this is an economic C example, so maybe you'll like it. So let's say like you're trying to figure out how much consumption increases. So this is consumption, right? Consumption. And how much it increases, how much it responses with income. So it makes sense that like consumption would change with income, right? With a higher income, you would spend more. And there is a minimum amount you'll spend even if your income was like 0, right? So over here, this would be your beta naught. So beta naught, the literal definition is that when your x value, well, over here this is x, but it's like y for income. So when your income is 0, how much are you going to consume anyways, right? And then over here you would have a line, and so this line is beta 1c, right? So you could like approximate, sorry, mistake. You can approximate your consumption based on B0 plus B1y. Does that make sense? But then the issue is that it's not going to look like exactly these values. So it's going to look like this, right? So how do I tell which line to draw? The way I tell which line to draw is by I minimize these squared errors away from this line. So if there is another line that is closer to these lines and further to other lines, you just try to minimize the squared error so that the line, so this would be the line of best fit. So the line of best fit is where it would slot itself exactly in, not really in the middle, but it would slot itself there. Part of the problem of these lines of best fits is let's say that you have a really low value over here. So we would call this a point of high leverage. So this would be an outlier, right? But then this single outlier can actually turn the entire line downward to sort of creates like a pull towards this value, because now they're like it's realizing that, oh shit, if it's all the way up here, my sum of squared error for this term is ginormous. So what this like pulls the entire line towards it to normalize downwards, basically. Yeah. So that's like that would be considered a point of high leverage. And in general, when you minimize the SSE, like the sum of squared errors, which was like the value in between like the point over here. Okay, I'll just write out the formula. So SSE equals to I equals to 1 yi minus yi hat. Okay. And so I'll redraw the graph so that I'll show you exactly what yi and yi hat are. So over here, this value is yi. For this value, this would be yi hat. So yi. And then this difference would be vi. So over here, same thing. And then over here, same thing. So you're moving a lot like this. This is basically how a regression is conducted. Literally, the program is just trying to force fit in a line in the middle. And if you do econometrics, you'll see that there are a lot of funky ways for you to find this line of best fit, which basically has a lot to do with like equations. I'm not sure did y'all cover the equations of how did you derive a line of best fit? Okay, well, oh, really? Okay. Yeah, so let me see if off the top of my head I know that. Yeah, okay. Wow, this is like my metric. Okay. So the way that it works is that give me a second. Let me find, because we did it in a very linear algebra way in econometrics, but I don't think that doing it in a very linear algebra way is always the best way. Let's see. For least square regression, did you use do you use like linear algebra to solve it? Okay, so basically how this works is that, give me a second. Yeah, okay, I found it. Okay, I think this is a little bit too technical. Yeah, okay, maybe not a good idea. Yeah, okay. Well, basically, oh, you use calculus. Okay, because the way that we learned it is all the UTs have to add up to 0. And so since all the ETs add up to 0, like this, like the sum of all the ETs, and I equals to 1 EI equals to 0. This EI equals to NI minus 1. This is YI minus B0 minus B1 XI. This equals to 0. Not only that, but this, if you multiply it by XI again, this YI minus B0 minus B1 XI, this also equals to 0. So now you have two formulas for XI, for for B0 and B1. And so you solve these two. Did you do it in the same way? Yeah, okay, great. Then yeah, I mean, if you want me to go over this, like basically from here, well, they kind of turn it into matrix notation, but then if you take the derivative with respect to x and then you set it to 0, and then you take the derivative with respect to y and then set 0, then when you equal out everything, then you get your estimators. Yeah. And I guess like something that's also important to know is that we need to know that SSE divided by n minus k minus 1, this equals to SE squared. And this is how you conduct hypothesis testing. So I guess like maybe I can go over regression hypothesis testings. Or if you want, I can cover like dummy variables or like adjusted R squares. Because like I don't think at this point I have the time to go through everything. So like if you could mention what you would prefer me to go through, that would be great. Dummy variables. Okay. Dummy variables are kind of a pain, but they're also amazingly useful. So dummy variables, the way that they work is that, let's say you're trying to figure out if wages are correlated with your race or your gender, right? And this is like obviously a question that economists would be interested in answering and knowing. So how would we, but then like there's no continuum on which you have a race or you have a gender. Like in the sense that like, I guess like, yeah, oh wow, this is really not equity minded, but under the assumption that there are only two genders, it would either be a 1 or a 0, right? Maybe I should use a different example. Oh, whatever. Okay. I guess like, yeah. Equals to. So over here, what you would want to create is you would want to create like a 1, 0 variable, right? So 1, let's say that this is F. So 1 is if you're female, 0 is if you're not. Okay? So 1 if female, and then 0 if not. Okay? And so basically what you're trying to do is that now what you have is you have a beta 0 plus a beta 1f. So how is it going to fit this in? So for all the non-females, you will have a situation where f equals to 0, right? Then you would have your wages equals to beta naught. And this is how you find your estimator if you're not female. If you're female, then S equals to 1 if you're female. So then your wages will equal to beta naught plus beta 1. So over here, what you actually see is that beta 1 is the difference in wages between females and non-females. And so that's where you get the power of like, okay, this is the difference in wages between females and non-females. Does that make sense? And then that's where you also have something called an interaction term. So let's say if you're like a, I guess like I'll change this to, okay, yeah, no, I still need the female example for the interaction. And then like, let's say you are like then you have another term, which is that you are a minority, like a racial minority. So I'll call that M. So M is 1 if minority and 0 if not. If you just leave it like this, it doesn't really work. And the reason why is that when you have a female, then you would have beta 0 plus beta 1. When you have a minority, like if you have a not female minority, okay, female not minority, then you would have beta 0 plus beta 1. Then let's say you have a not female minority, then you would have beta 0 plus beta 2. When you have not female not minority, you would have beta 0. And then when you have female minority, you would have beta 0 plus beta 1 plus beta 2. But then here lies a problem, right? Your beta 2 is conditioned on like not female minorities. Your beta 1 is conditioned on female not minorities. And your beta 0 is conditioned on not female not minorities. So adding this up is assuming that the only effects that they have on wages is that like if the female term and the minority term. But it's entirely possible that if you're like a female minority, that your wages are actually lower than like regular than like non-female minorities and lower than like females that are not minorities. And that is why you need to create an interaction term. So this is where you have beta 3 FM. And so if you are both a female and a minority, then this will equal to 1, this will equal to 1, and then you suddenly get a beta 3 term that conditions on this. And so now you can truly see the difference between like now you have its own separate term just for this category. And this is why you need the interaction terms, because otherwise you're assuming that it's the same effect. Like if like, okay, like let's say if you have a female that's not a minority and not a female that's a minority, if you add up the effects, it should be similar to the effect of like a female that is a minority, but that's not always necessarily the case. And when that's why the name interaction term comes in. So how does being a female and being a minority interact together to either increase or decrease your wages? That is where you would need this extra term. So any single dummy variable that you have, every other pairing, if you want to do it properly, every single pairing has to have an interaction. So let's say I introduce another variable, like dummy variable. Let's say, let's make this one really arbitrary. Okay, I guess like we could say like C would be something like class 1 high income. No, sorry. 1 low income and 0. Wait, that's just wages. Okay, 1. 1 has a cat. 0 does not have a cat. I'm sorry, I could not be more creative than this. This is just to illustrate the fact that if you're adding beta 4C, you also need to be adding beta 5 FC plus beta 6 MC. So for all of them, you need an interaction term. Yeah, and then you could write down all the categories, and that's basically how a dummy variable would work. I would think that it's a rather neat trick and very powerful because there's a lot of different types of categorical data that you want to be able to classify in this manner. But without dummy variables, it's like, okay, how do you deal with like a yes or no situation? And so this is basically how you deal with a yes or no situation. Yes, we take this value. So like female, yes, okay, we take this. Female, yes, we take this. Female, yes, female, yes, we take this. Are they a minority or not? Okay, let's say they're not a minority, so we can cancel these two out. Do they own a cat? Oh, yes, they own a cat, so we can take this term and this term, and then remove this term, because they're not a minority. And I guess also another important thing to note is that over here, you're assuming a default state. So your default state under these circumstances is when everything else is 0, right? So my default is that if you're not a female, you're not a minority, and you do not have a cat. But then you cannot, like, this is your default person. You cannot introduce another constant term like 1 plus something else, as you sometimes would in other regressions, because otherwise you'll be creating collinearity. So I cannot create like if I go back to the like reduced example, let's say I create a variable for like, okay, let's say I create wages equals to beta naught plus beta 1 has a cat, and then I create a third variable n, which is 1 does not have a cat and 0 has a cat. You would think that this would create better outcomes, right? Because like I'm like, okay, if they have a cat, then I will put it as C. If they don't have a cat, then I would have N, right? But then the situation is such that you would have collinearity because C and N, when you add them up together, you get 1 because everyone either has a cat or doesn't. So if you add C and N together, so it's like, let's say I have a cat, and then which means that I'm 0 on not having a cat. You don't have a cat, which means you're 1 on not having a cat. So this goes on and on, right? When you add them all up together, it becomes 1 all the way down. And this introduces collinearity. So we cannot have a situation where we have a dummy variable does not have a cat. It's either it has a cat or the default is beta 0. So we cannot have this extra term. Does that make sense? Okay, amazing. Is there anything else that you want me to cover? Or are there any other questions that you have with regards to the material? I'm sorry that the example was really bad. Like, I don't remember exactly what Shaori mentioned the first time I took the class. So. Is there anything else you'd like me to cover specifically? If not, I will keep going with like a eclectic mix of things. Because like I think that the F test and the T test is done in the exact same way. All you're doing is plugging in S square of E instead of the regular version. So I guess like something that I would want to mention is like something that seemed rather esoteric when I first saw it was like the adjusted R square. So this adjusted R square is 1 minus the sum SSE divided by N minus K minus 1 divided by S plus N minus 1. Oh, Sarish, yes, what's up?
Are you just taking questions right now?
Yes.
Okay. So something that he kept going over in class
Yeah.
is the law of iterated expectations and the law of total variance. And we're not like it didn't show up in the textbook problems and the homework problems, but we're not sure how to use them to like get the proofs. Like in what ways would they be introduced in an exam?
Log iterated expectation of log total variance.
Both the law of iterated expectation, the law of total variance.
Ah, law of total iteration and law of total variance. How would you use that in statistics? How would you use that in statistics? Huh. These are usually more probability related concepts. Did he cover any like conditional regressions or anything? Law of total expectation. Ah, okay. I can see why you would use law of total expectation. Okay.
Law of total variance?
Sorry?
Law of total variance. Or law of iterated expectations, yeah.
Yeah, the reason why you would use it is because let's say I want to take the expectation of X. This is one of our regressors, right? Multiply by U. Okay? How would I find this? Well, I would use the law of total expectation, which equals to expectation of x u given.
Sorry.
Sorry.
Law of iterated expectations, not total.
Yeah.
I don't know if. Okay. It comes into play.
Yeah. So over here, we create this situation, right? And then afterwards, you can see that this term x, like you're conditioning on x, which means that you can bring it out. So expectation of x given the expectation of u given x. And then over here, you notice this has to be equals to 0 because this is one of the assumptions of having a regression. And so this results in expectation of x 0, which equals to 0. And so this is actually one of the situations where I would see the law of total expectation being used a lot, at least in like regressions classes. It's always this same old story over and over again. When you have things that are like dependent on, like when you have these two things, and then one is like, you have this like this is called the exogeneity assumption. So given x, this u would be 0 because the expectation of u equals to 0 anyways. And this x is assumed to be exogenous for you to be able to run a regression. So this exogeneity assumption results in the expectation of x times u being 0. And then this helps you solve for like a best linear unbiased estimator because like you can basically show that like the bias term goes away because x multiplied by u is 0, like the expectation. Does that make sense?
Yeah.
Because this is CI.
What
Sorry?
about total variance?
Let me see what the law of total variance is first, and I'll see where I've seen it. Law of total variance. I have never seen this used before. I don't think it's that useful. Like, I think I've seen it literally entirely once in the econometrics class. So I think without knowing it, it will be fine. But did he mention, what context did he mention it under?
Many when we talked about like just like getting the variance of different coefficients.
Getting the variance of different coefficients. Huh.
Law of total variance.
Yeah.
Yeah, I guess I've never seen it much before, but if you show me those exact examples, like, but I mean, if you know the examples, then you kind of know it. It's just that I don't really see how, because you can get around using the law of total variance by expanding it into covariances anyways. So like it doesn't like, sorry, by expanding it into like expectations anyways. So it's kind of like a special version of the law of total expectation. And so I think that that's why we've never really seen it much. But like, under what circumstance did he use it?
The variance of summation AI error I given xi to xn equals variance of expectation of some summation of AI error I given x1 to xn plus expectations of variance of variance of summation AI error I.
You
given
could
x.
send me the screenshot and then I'll tell you why it would work, I guess.
Can I send it to you on Messenger?
Yeah, sure.
If this is 0,
Sent.
Okay, awesome. Variance, law of variance.
There's a second part I sent as well.
Okay. Ah, I think why I've never seen this much before is that we were given that like under the conditions of like homoscedastic variances, all you really need to do to get the variance of something, variance of it's the summation of AI with epsilon I. Summation of AI with epsilon I given xi xn. So over here, what we would have assumed was that this would be like epsilons would be uncorrelated with x1s. So then that would be the expectation for this would be 0, right? And so if we turn this variance term into, oh yeah, I mean like, yeah, that's what it's doing. Yeah. Yeah, I guess like it was I guess like in this way you're deriving the rule where you would figure out that this equals to sigma squared, and then there's like this like big covariance matrix. Yeah. AI squared. This is like the, I guess, yeah, that's the derivation of it. I think that that would be the only time where you'd see the law of total variance, because once you have proved that the reason why it works is basically when you have something with an expectation equals to 0 of this, right? Then the variance, the way I would do it anyways, the variance of AI EI equals to the mean of square minus the square of mean. So this would be the mean of the square AI epsilon I square minus the square of the means AI square epsilon I square. And I take this and square it. Oh, these are all they have to have the conditionals over here. And then the conditionals over here. But then we know that this conditional expectation over here equals to 0 squared. And then we know that this term, equals to the expectation of the sum of AI squared, because this is independent, right? And so then we would get the exact same thing basically in the same way. So I guess like under this circumstance, I wouldn't use the law of total variance, but you could totally use the law of total variance as well. Like, does it make sense?
You said you'd use the law of total variance, but instead you could use what? Like, can you repeat that?
So what you're using is that the variance of x equals to the expectation of x squared minus expectation of x, the whole thing squared. right?
Mhm.
When this expectation of x, the whole thing squared, is 0, then you are left with this term only. When you're left with this term only, then you can get this.
Okay. One last thing, and it's I don't know if we use it, like why I wanted to ask you about the law of total variance is we don't know if we can use it to solve this question we're kind of just stuck on from one of the homeworks.
Which one?
I just sent it to you, question 2.
Question 2.
Yeah. In terms of 11.1, 11.15 and 11.16, I don't think it's relevant. All 11.15 was just explain the difference between residual EI and model error EI. But we just don't, we're kind of having trouble making this proof, I guess.
Following the same idea. What is 11.15?
So 11.15 is a question from the homework, and all it is explain the difference between the residual EI and the model error EI.
Okay, I should probably stop the recording as well. Give me a second.